A vast cold patch stains the universe's oldest baby picture. This is the cosmic microwave background cold spot, a cosmic anomaly so strange it threatens to rewrite our understanding of everything. By the end, you will know the three leading theories that could explain this mystery, from a billion light-year void to a bruise from another universe. We will explore whether it is a flaw in our maps, a crack in space-time, or evidence of a reality beyond our own. What does it feel like to discover a crack in the foundation of the cosmos? To see the cold spot, we must first learn to read the sky's oldest message. Think of the universe not long after its fiery birth, a seething plasma of particles and light so dense that photons could not travel an inch without colliding. For nearly 400,000 years, it was an opaque, glowing fog. Then, in a pivotal moment, the cosmos expanded and cooled just enough for a fundamental change. Electrons combined with protons to form the first neutral atoms, and in that sudden clearing, the light that had been trapped was finally set free. That first flash of liberation has been traveling ever since, stretched by the expanding universe from visible light into the microwave part of the spectrum. We detect it today as a nearly uniform glow from every direction, a cosmic hum at just under 3 degrees above absolute zero. This is the cosmic microwave background, the afterglow of creation itself. It is the most perfect blackbody radiation ever measured, a snapshot of the infant universe when it was a mere 380,000 years old. But perfection in cosmology is not where the interesting stories lie. When scientists created exquisitely detailed maps of this background, they found it was not perfectly smooth. There are incredibly subtle wrinkles in this ancient fabric, tiny variations in temperature of about 100,000th of a degree. These minute anisotropies are not flaws. They are the blueprint for everything we see. Slightly denser, warmer patches held the gravitational seeds that, over billions of years, would pull in matter to form galaxies, clusters, and the vast cosmic web. The pattern is a frozen record of the universe's initial conditions, and we have learned to decode it with astonishing precision. This makes any feature that breaks the expected pattern a profound mystery. The cold spot is not just another tiny wrinkle. It is a significant, extended region of space that is markedly cooler than its surroundings, a large, subtle dip in the temperature of the primordial light. In a map defined by statistical noise and predictable, small-scale variations, it stands apart. It is an anomaly written in the universe's first language, a language we thought we were beginning to understand. Finding it was like studying a vast, ancient manuscript, deciphering its consistent grammar and script, and then turning the page to find a single, sprawling symbol that obeys none of the established rules. What could possibly have left its mark on the very first light? That ancient manuscript, the cosmic microwave background, required a new kind of cartography to read its deepest secrets. The story of the cold spot's discovery is one of patient, meticulous measurement, a mystery that only revealed itself after we learned to see the universe in exquisite detail. For decades after its initial detection, our maps of the primordial glow were coarse, like a weather satellite image of an entire continent. We knew the general climate, but we could not see the local storms. This changed dramatically with two pioneering space missions. First, NASA's Wilkinson Microwave Anisotropy Probe, launched in the year 2001, spent 9 years scanning the entire sky with unprecedented sensitivity. It produced a map of the cosmic microwave background so detailed it felt like putting on a pair of glasses for the first time, revealing the subtle texture of the infant cosmos. But the story did not end there. The European Space Agency's Planck satellite, launched in 2009, was an even more refined instrument. Think of it as a cosmic audiophile's dream, designed to listen to the universe's oldest hum with minimal static. Planck measured the temperature variations across the sky with a precision of a few millionths of a degree, creating the sharpest, most reliable baby picture of the universe we have ever seen. With these magnificent maps in hand, cosmologists did not simply look, they listened for a discordant note. They employed sophisticated statistical tools, algorithms designed to sift through the sea of data and identify patterns that strayed from the expected cosmic symphony. The universe's initial conditions, according to our best models, should produce a random, Gaussian distribution of hot and cold patches like the static on an old television screen, following predictable statistical rules. The analysis was a search for an outlier, a region that broke the statistical mold, and in the constellation Eridanus they found it. The anomaly was not just cold, it was coherent. It spanned a staggering diameter of about 1.8 billion light-years, a continent of coolness on the cosmic map. Its temperature dip, while incredibly subtle at roughly 70 microkelvins colder than the average, was significant given its vast scale. Calculating the odds, researchers found that such a large and cold feature has only about a 1 in 50 chance of appearing in a universe that perfectly follows our standard cosmological model. In the world of fundamental physics, where discoveries often require odds of 1 in millions, a 1 in 50 chance is a blaring siren. It is not proof of a breakdown, but it is a powerful, persistent whisper that something in our story might be missing. This was no longer just a curious blotch on the map. It was a formal anomaly, a cosmic question mark demanding an answer. So what could carve a billion light-year-wide depression into the fabric of space-time itself? The investigation had truly begun. This perfect cosmic blueprint, our Lambda cold dark matter model, now faces a puzzling contradiction. Think of this model as the most successful instruction manual for building a universe we have ever written. It tells a compelling story. In the first fractions of a second after the Big Bang, a period of hyper-expansion called inflation stretched microscopic quantum jitters into vast cosmic-scale ripples. These ripples in density became the gravitational seeds for everything to come. The pattern imprinted on the cosmic microwave background should therefore be a mostly random, Gaussian distribution of these seeds. It should look like static, with hot and cold patches of various sizes following very specific statistical rules. We do expect some rare flukes, a particularly large warm patch here or an unusually cold one there, simply by the roll of the cosmic dice. But the cold spot is not playing by those dice. Its problem is threefold. It is exceptionally large, spanning a region nearly 2 billion light-years across. It is notably cold, a deeper temperature dip than its vast area would typically allow. And perhaps most intriguingly, some analyses suggest it is surrounded by a subtle ring of slightly warmer material, like a cosmic crater with a raised rim. This combination of features pushes it into the territory of an extreme statistical outlier. In the precise language of cosmology, some studies rate it as a 5 sigma event. This means the probability of such a feature arising naturally within our standard model is vanishingly small, akin to flipping a coin and getting heads dozens of times in a row. The tension is now undeniable. We have a beautifully successful model that predicts the distribution of galaxies, the abundance of light elements, and the accelerating expansion of the cosmos. Yet, in the oldest light we can see, there is this persistent, quiet anomaly that does not quite fit. This forces a profound and uncomfortable choice upon scientists. Is the cold spot simply that 1 in a billion cosmic coincidence, the rare statistical fluctuation that we, by sheer luck, are here to observe in our particular corner of the sky? Or is it something far more significant? Could it be a signpost, a crack in the elegant facade of our standard model, pointing toward new physics or an exotic phenomenon we have not yet dreamed of? The hunt for an answer begins not with wild speculation, but with the most logical, sober explanation of all. What if our maps are deceiving us? The simplest answer is often the most appealing. Perhaps the cold spot is not a flaw in the ancient light, but a shadow cast by something much closer to us in cosmic time. This leads us to the first and most logical theory, the Supervoid Hypothesis. To understand it, we need to think about what happens to light on its epic journey across an expanding universe. Imagine a photon, a particle of that primordial afterglow, has been traveling for over 13 billion years. Its path is not through empty, static space. It is traversing the evolving cosmic web, a vast architecture of galaxy clusters and immense empty voids. According to Einstein's theory of general relativity, light gains or loses energy when climbing in or out of a gravitational well. This is called the Integrated Sachs Wolfe effect. In a static universe, the energy a photon loses falling into a gravitational well, like a cluster of galaxies, it would perfectly regain climbing back out. But our universe is not static, it is accelerating in its expansion. This cosmic acceleration changes the rules. When a photon enters a vast, deep void, a region of below-average density, it must climb out of a gravitational hill that is actually becoming shallower with time due to the universe's expansion. Because the hill flattens as the photon climbs, it does not get all its energy back. It arrives at our telescopes slightly more tired, slightly cooler than light that traveled a more average path. So, if an unimaginably large void, a cosmic supervoid hundreds of millions of light-years across with a startling lack of galaxies, sits directly between us and the cold spot, it could act as a colossal lens of coolness. This theory is elegant because it connects two eras. It ties the anomaly in the ancient cosmic microwave background to the large-scale structure of the more recent universe, the distribution of galaxies we can map today. It suggests the cold spot is not a message from the beginning, but a signature written along the way, a shadow of a great cosmic emptiness. The hunt then turned to a straightforward task. If this theory is correct, we should be able to look toward the cold spot and see the void. Astronomers began to map the galaxy distribution in that direction with great care, using massive surveys like the Sloan Digital Sky Survey. What they found was intriguing but far from conclusive. There does appear to be a notable underdensity in that region, sometimes called the Eridanus supervoid. But there is a serious problem of scale. The void we have observed, while large, is not nearly large or empty enough to explain the profound coldness and size of the cold spot through the integrated Sachs-Wolfe effect alone. The numbers simply do not add up. It is as if we found a small hill when our calculations demanded a missing mountain. This leaves the supervoid hypothesis in a difficult place. It could be a partial contributor, a piece of the puzzle, but it struggles to be the complete answer. If a simple shadow from an empty region cannot fully explain this cosmic chill, then we must consider that the anomaly is not an illusion of the journey, but something fundamental about the destination itself. What if the cold spot is not a shadow, but a bruise? The search for a missing mountain of emptiness became a meticulous cosmic census. If the cold spot was a shadow, astronomers needed to find the object casting it. They turned their most powerful surveys toward the constellation Eridanus, cataloging millions of galaxies to map the three-dimensional structure of space in that direction. The initial findings from projects like the Sloan Digital Sky Survey were tantalizing. They hinted at a broad region with fewer galaxies than expected, a potential supervoid hundreds of millions of light-years across. For a moment, it seemed the mystery might have a straightforward solution. Yet as the data improved and the analysis deepened, the clear picture began to blur. Later, more comprehensive surveys painted a conflicting portrait. Some research groups, using different statistical methods or deeper observations, argued that the proposed void was not a true cosmic anomaly. They found that while the region might have a slightly lower density of bright galaxies, it was not the profound, echoing emptiness required by the theory. The galaxy count, they concluded, was not anomalously low enough to explain the profound chill in the ancient light. This created a frustrating stalemate at the heart of modern cosmology. On one side, the cold spot signal in the cosmic microwave background is clear and statistically significant. On the other, the evidence for a supervoid of the necessary scale and depth is murky and contested. The numbers present a stark challenge. To produce the observed cooling through the known physics of the integrated Sachs-Wolfe effect, any void would need to be almost unbelievably vast and starkly empty, pushing the boundaries of what our models of cosmic structure formation allow. We expect voids in the cosmic web, but not voids of this extreme character. So we are left with a difficult choice. Perhaps our galaxy surveys are still incomplete, missing faint galaxies or tracing structure in a way that obscures the true depth of the void. Or perhaps the void is simply not there, and we are forced to admit that the shadow hypothesis, for all its elegance, cannot fully account for the anomaly. This evidentiary conflict forces a pivotal question. If the cold cannot be explained by an absence in the foreground, might it instead be a signature of something far more exotic, woven into the universe's foundation from the very first moment? This pushes us toward a theory that is far more exotic, a possibility written not in the absence of matter, but in the very geometry of reality. If the cold spot is not a shadow, perhaps it is a scar. Some cosmologists propose it could be the fossilized imprint of a cosmic defect, a kink in the fabric of spacetime that formed in the universe's first chaotic moments. To understand this, we need to picture the newborn cosmos not as a smooth, empty stage, but as a seething ocean of fundamental fields. As the universe expanded and cooled rapidly after the Big Bang, these fields underwent dramatic phase transitions, much like water freezing into ice. And just as ice can form with cracks and fissures as it solidifies, spacetime itself might have crystallized with imperfections. These are called topological defects, and one particular type, known as a texture, offers a compelling culprit. Imagine a vast, invisible knot in the fields that define our reality, a tangled region where the rules of physics are subtly twisted. Such a texture would have immense gravitational influence. As the primordial light of the cosmic microwave background passed near or through this cosmic knot, the texture's peculiar gravity would have done something strange. It would have effectively given photons a slight gravitational boost, a nudge that counterintuitively would make them appear cooler to us today by the time they finished their 13-billion-year journey. This process, related to what physicists call the Sachs-Wolfe effect, would leave a very specific signature, a circular, cold patch with relatively sharp edges, potentially surrounded by a faint, warm ring, a description that matches the cold spot's observed profile remarkably well. This theory is powerful because it provides a natural explanation for the anomaly's clean, coherent shape and its stark temperature contrast. It does not require the improbable coincidence of a perfectly aligned supervoid. Instead, it suggests the cold spot is a direct snapshot of a dramatic event in the early universe's cooling process, a frozen moment of spacetime itself cracking into its current form. The texture hypothesis transforms the cold spot from a puzzling shadow into a potential relic, a cosmic fossil offering us a glimpse into forces and transitions that occurred a fraction of a second after everything began. Yet, if such a dramatic defect exists, woven into the cosmos's foundation, what other imprints might it have left? The search for corroborating evidence would lead astronomers to look not just at the ancient light, but at the modern distribution of galaxies, seeking other signs of this primordial scar. The texture hypothesis ties the cold spot to a moment of profound cosmic change, a time when the laws of physics themselves were settling into their current form. To grasp this, we need to think about the forces that govern our universe not as fixed and separate, but as aspects of a deeper unity. In the unimaginable heat of the very first instance, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been indistinguishable, woven together as a single, symmetrical superforce. This is the realm of grand unified theories. Then, as the cosmos expanded and cooled, it underwent a series of dramatic shifts, much like water turning to ice. With each drop in temperature, a symmetry broke. The unified force fractured, first separating the strong nuclear force, then later the electroweak force splitting into the electromagnetic and weak forces we know today. These were cosmic phase transitions, moments when the entire universe changed its state. Now, think of a pond freezing over on a cold night. As the ice crystals form and grow, they often meet in misaligned patterns, creating cracks and fault lines in the surface. The universe may have frozen in a similar way. As it cooled through these monumental transitions, the fields that dictate reality could have crystallized with imperfections, topological defects frozen into the fabric of spacetime itself. These defects come in different forms. Cosmic strings are like infinitely thin, incredibly dense cracks, cosmic scars of pure energy. Domain walls are immense, sheet-like barriers separating regions of space with different properties. And textures are more like grand, three-dimensional knots in the fields, regions where the fields cannot smoothly align. Most of these exotic structures would have been unstable, collapsing or diluting away as the universe continued to expand. But a rare, exceptionally large texture could have survived long enough to witness the release of the cosmic microwave background. Its presence would warp the local geometry of space. When the primordial photons from that first light passed through this knotted region of spacetime, they would have experienced a subtle gravitational shift. Climbing out of the texture's unique gravitational landscape in an expanding universe, they would lose a tiny bit of energy, arriving at our telescopes just a little cooler than their neighbors. This creates a distinct circular signature in the ancient light, a cold spot with a potential warm ring, a fossilized imprint of a crack in reality's foundation. This theory elevates the cold spot from a curiosity to a potential relic of the highest energy physics, a direct signal from an era of unification that no particle accelerator on Earth could ever hope to recreate. It suggests we might be looking at a fossil from the moment the forces of nature chose their separate paths. Yet, if such a monumental defect exists, could it have left other traces across the cosmos, and how would we ever know for sure? Yet if a texture is a scar from our universe's birth, the third theory proposes something far more profound. It suggests the cold spot is not a scar at all, but a bruise inflicted from outside our cosmic bubble. This is the multiverse collision hypothesis, a concept that stretches the imagination to its very limits. Our leading theory for the universe's initial explosive growth is called inflation, a period of faster-than-light expansion that smoothed and stretched the cosmos. But some versions of this theory, known as eternal inflation, propose a staggering consequence. In this view, inflation never truly stops everywhere. Instead, our entire observable universe is just one bubble that stopped inflating within a much vaster, eternally inflating multiverse. Picture a pot of boiling water, endlessly bubbling. Each steam bubble that forms and rises is its own self-contained universe, with its own laws of physics, popping into existence within an incomprehensible, frothing sea of spacetime. In such a reality, these bubble universes are not stationary, they expand, and if two of them form too close together, their expanding boundaries could eventually meet and collide. The energy released in such a cataclysmic meeting of realities would be beyond anything within a single universe. Now, consider the timing. If this collision occurred before the release of the cosmic microwave background, that is, before our universe was 380,000 years old, the immense energy of the impact would have left a distinct mark on that primordial plasma. As the shockwave from the collision reverberated through our infant cosmos, it would have heated and stirred the particles in a specific, vast region. When the universe finally became transparent and released its first light, that disturbed region would appear different. The physics suggests it could create a circular area in the cosmic microwave background with an unusual temperature profile, a kind of cosmic fingerprint from another reality. Remarkably, the cold spot's large, coherent, and somewhat circular shape, along with the subtle warm ring some analyses detect around it, fits the predicted profile of such a collision signature. This idea transforms the cold spot from an internal anomaly into potential evidence of an external event. It would no longer be a flaw in our universe's blueprint, but a signpost pointing to a cosmos of unimaginable scale, a multiverse where our entire reality is just one island in an infinite archipelago. The chill we detect would then be the fading warmth of a long-ago encounter with another universe entirely. Of course, this is the most speculative of the three leading theories. Proving it seems a monumental, perhaps impossible task. How do you find evidence for something that exists by definition, outside everything we can ever observe? The answer may lie not in looking for the other universe, but in looking for other bruises. If our bubble was bumped once, it might have been bumped multiple times. Astronomers would then scour the rest of the cosmic microwave background map, searching for other, similar anomalous patches that could be the scars of other ancient collisions. Finding a pattern of such features would be a hint that we are living in a surprisingly crowded neighborhood within the multiverse. So we are left with three distinct possibilities, each more incredible than the last. A statistical fluke, a cosmic fossil from the first moments, or a bruise from another reality. The investigation into this strange cold patch has become a journey to the very edge of scientific inquiry. This idea forces us to think not of one universe, but of a cosmos of cosmoses. The theory of eternal inflation paints a picture far grander than the single expanding bubble we call home. It proposes that the hyper-expansion we call cosmic inflation is not a one-time event that ended everywhere. Instead, it is the default, endless state of a vast underlying reality, a kind of seething, energetic metascape. Within this eternally inflating background, random quantum fluctuations can trigger local pockets where inflation stops. Each of these pockets becomes its own self-contained universe, bubbling into existence with its own potentially unique laws of physics, forever separated from the inflating sea around it by a blistering high-energy wall. In this view, our entire observable cosmos is just one such bubble among an infinite, frothing multitude, a single soap suds in an ever-growing cosmic sink. Now picture two of these bubbles forming relatively close together in this chaotic metascape. As each bubble universe expands at a staggering rate, their boundaries, those energetic domain walls, would eventually race toward one another. When they meet, it would be a collision of realities. The energy released would be titanic, far exceeding anything possible within the orderly physics of a single, settled universe. If such a collision happened in our cosmic infancy before the release of the first light, it would have sent a shockwave rippling through the hot, dense plasma of our bubble. This immense disturbance would have stirred and heated that primordial soup in a specific, vast region. Later, when the universe became transparent and released the cosmic microwave background, that disturbed zone would freeze into the sky as a distinct anomaly, a circular imprint of the impact. The cold spot, with its large scale and reported ring-like features, fits the predicted profile of such a cosmic bruise. While this remains the most speculative of our three explanations, it carries a profound implication. It would elevate the cold spot from a puzzle within our universe to the first potential empirical clue of a reality beyond it. We would not just be studying an anomaly, we might be holding a piece of evidence for the multiverse itself, a fading scar from a time when our bubble was not alone. Yet the question remains, how do we decide if this is a true discovery or just cosmic noise? The answer lies in the rigorous, often unseen, world of statistical cosmology. This is not about gut feelings or striking images. It is about cold, hard probability. Scientists do not simply look at the cold spot and declare it strange. They must quantify its strangeness, measuring it against the expected backdrop of a perfectly random universe. To do this, they employ powerful mathematical frameworks. One key approach treats the cosmic microwave background as what is called a Gaussian random field. Imagine you are listening to static on a radio. That hiss is a Gaussian random signal, meaning its variations follow a very specific bell curve pattern of probability. The primordial universe, according to our standard model, should resemble that static, a random tapestry of hot and cold patches with predictable statistical properties. Spherical harmonic decomposition is another essential tool, a mathematical way of breaking down the sky map into its constituent waves, much like identifying the individual notes that make up a complex chord. By applying these tools, cosmologists can ask precise questions. Not just, is this region cold, but how cold is it compared to every other region of similar size? What is the probability that the coldest spot in the entire sky would be this large and this pronounced? The results are fascinating because they are not unanimous. Different statistical tests, each probing a different aspect of the cold spot's personality, tell slightly different stories. A test focusing purely on its vast diameter might suggest a 1 in 50 chance of such a large feature appearing at random. A test scrutinizing its temperature profile, including hints of a surrounding ring, might push the odds down to less than 1 in 100. Other analyses, searching for the single coldest point anywhere on the map, yield probabilities around 1 in 200. None of these on their own reach the gold standard of 5 sigma, or a 1 in 3.5 million chance that particle physics requires for a definitive discovery. But collectively, they paint a compelling portrait of an outlier. The cold spot consistently ranks in the top percentile of weirdness across multiple independent tests. This is why it is taken so seriously. It is not a fluke identified by one single metric. It is a persistent anomaly that shows up as unusual again and again, wearing different statistical hats. The core challenge here is fundamental to all cosmology. We have only one universe to observe, one single dataset. When you are analyzing a map with millions of pixels, representing billions of light years, you are absolutely going to find some rare-looking features purely by chance. It is the cosmic equivalent of finding a face in the clouds. The human brain is wired to seek patterns. The job of statistical cosmology is to be the stern referee, to calculate whether the face we see in the cosmic static is so detailed, so improbable, that it likely indicates something real underneath. For the cold spot, the referee has not blown the whistle to stop the game, but has certainly called for a video review. The evidence is under scrutiny, and the outcome will determine whether we are seeing a magnificent statistical coincidence or the first crack in a much larger truth. But before we can accept a cosmic bruise or a primordial scar, we must first be certain the spot is even on the cosmic map. Could it be a smudge on our telescope's lens, a fingerprint left by our own galaxy? Every great cosmic mystery begins with a process of elimination, and the first suspect is always the foreground, the cosmic clutter that sits between us and the ancient light. Our view of the pristine cosmic microwave background is not through a clear vacuum. We are peering out from within the bustling disk of the Milky Way, a region filled with its own fog and static. Vast clouds of interstellar dust, grains of carbon and silicate smaller than a wavelength of light, drift through the galactic plane. When illuminated by starlight, this dust re-emits energy in the microwave part of the spectrum, creating a faint, diffuse glow. Furthermore, our galaxy is threaded with powerful magnetic fields. Electrons, spiraling at nearly the speed of light along these magnetic field lines, produce a different kind of microwave emission called synchrotron radiation. Both of these galactic foregrounds create their own patterns of warmth and coolness on the sky, a layer of local noise that could, in theory, superimpose a cold patch onto the deeper cosmic signal. If the cold spot is simply an artifact of this galactic haze, then the entire mystery evaporates. It would be an illusion, a shadow cast by a dust cloud in our own cosmic backyard, not a message from the edge of reality. Ruling this out is not a simple task, it is a cornerstone of modern cosmology. Missions like Planck were designed with this exact challenge in mind. They did not observe the sky at just one microwave frequency. They mapped it across 9 different frequencies, from 30 to 857 GHz. This multi-frequency approach is the key to the cleanup. Think of it like listening to a distant radio station through heavy static. The static from our galaxy has a very distinct sound, a specific spectral signature that changes predictably with frequency. The true cosmic microwave background, however, has the unique signature of a perfect blackbody, its sound consistent across a broad range. By comparing the maps at all these different frequencies, sophisticated algorithms can isolate the various components, like separating voices in a crowded room. They can build a model of the galactic dust emission, map the synchrotron glow, and then digitally subtract them from the total signal. What remains, in theory, should be the clean, primordial light. The results of this meticulous forensic cleaning are crucial. After the best models of galactic foregrounds are removed, the cold spot does not fade away. It persists, a stable and significant feature in the purified maps. This component separation analysis is a powerful argument against a local origin. It suggests the anomaly is not a fingerprint on our window, but something etched into the window pane itself, a feature embedded in the cosmological background. This rigorous process transforms the cold spot from a curious observation into a validated cosmic anomaly. By clearing the fog of our own galaxy, scientists have not solved the mystery, they have deepened it. They have confirmed that the question we are asking is not about our local neighborhood, but about the fundamental structure of the universe. The chill is real, and it is coming from a very, very long way away. The light from the dawn of time carries a hidden fingerprint in its very orientation. Beyond its subtle temperature variations, the cosmic microwave background is also polarized, meaning its light waves vibrate in a preferred direction. This polarization is not random. It is a direct imprint of the last frantic moments before the universe became transparent, created by the scattering of photons off the hot, swirling electrons of the primordial plasma. Scientists categorize these imprints into 2 distinct patterns, E modes and B modes. Think of E modes as a radial, curl-free pattern, like the lines of force emanating from an electric charge. These are primarily generated by the density fluctuations that seeded all cosmic structure. B modes, on the other hand, have a swirling, curl-like character, reminiscent of the pattern around a magnetic pole. While some B modes are created by later effects like gravitational lensing, a specific type of primordial B mode could be the holy grail of cosmology, a direct signature of gravitational waves from the inflationary epoch. For the cold spot, this polarization data offers a powerful, independent test. If the anomaly was caused by a cataclysmic early universe event like a texture or a bubble collision, the immense energy and gravitational disturbance would have left a specific, correlated stamp in the polarization patterns around its borders. It would be like finding not just a crater, but a distinct pattern of shock waves frozen in the surrounding rock. The search for this complementary signature has become a critical front in the investigation. Teams have meticulously analyzed polarization maps from the Planck satellite and from powerful ground-based observatories like the Atacama Cosmology telescope in Chile. So far, the results are inconclusive. No definitive, unique polarization signal has been robustly linked to the cold spot's location. This absence is not a dismissal of the exotic theories, but it does raise the bar. It means that if a texture or a collision is responsible, its polarization signature might be fainter than predicted, or perhaps our current maps are still not sensitive enough to tease it out from the cosmic noise. This sets the stage for the next generation of experiments, future observatories designed with exquisite sensitivity to polarization will scan the skies with even finer resolution. They will be listening for that faint, swirling whisper in the ancient light that could confirm a dramatic story of cosmic defects or a clash of universes. Until then, the polarization data remains a silent witness, holding a potential answer we have not yet learned to hear. The cold spot's strangeness is magnified by a startling fact: it is not an only child. Across the vast map of the primordial sky, astronomers have identified a small family of other large-scale anomalies, each one quietly defying the expectation that the universe should look the same in every direction, a principle known as statistical isotropy. This is the bedrock assumption of our standard model, the idea that there are no special places or preferred axes in the cosmos. Yet the evidence suggests our universe might have a subtle handedness, a faint grain like cosmic wood. One of the most significant of these siblings is called the hemispherical power asymmetry. Imagine dividing the cosmic microwave background map in half along a specific, mysterious axis. On one side, the temperature fluctuations, those tiny wrinkles from the infant universe, are noticeably stronger and more pronounced. On the other side, they are gentler, quieter. It is as if the universe's volume knob was turned up in one hemisphere and down in the other at the moment of its first light. This is not a dramatic visual feature like the cold spot, but a subtle statistical imbalance that emerges only after painstaking analysis of the entire sky. Then there is the curious case of the low multipole alignment, a finding so peculiar it earned the playful nickname the axis of evil. In the language of cosmology, multipoles are mathematical descriptions of patterns on a sphere. The lowest multipoles represent the very largest possible structures in the sky, the broadest strokes of the cosmic canvas. According to our standard model, these grand patterns should be oriented randomly, pointing in no particular direction. Yet when scientists measure them, they find an unsettling coherence. Several of these largest scale patterns appear oddly aligned with one another, and even with the plane of our own solar system. This alignment is deeply puzzling because it hints at a preferred direction in the cosmos, a cosmic north that should not exist. It also raises an uncomfortable, almost philosophical question. Could there be some unnoticed contamination from our local environment, or is this a true feature of the universe itself? Each of these anomalies, the power asymmetry, the aligned multipoles, and of course our cold spot, can be studied and debated on its own. Each has its own possible explanations, from subtle measurement biases to exotic new physics. But their collective existence is what truly gives cosmologists pause. Finding one strange feature in a dataset as vast as the cosmic microwave background could be a fluke. Finding several, each breaking the rules of isotropy in different but complementary ways, begins to feel like a pattern. It suggests that while our Lambda cold dark matter model is spectacularly successful at describing the universe from its Middle Ages to the present day, it might be missing a crucial piece of the puzzle when we look at the very largest scales of space and time. The cold spot is perhaps the most visually striking and localized member of this puzzling family, a single strange tree in what appears to be an increasingly unusual forest. Together, these anomalies whisper a provocative question: what if the universe is not perfectly smooth and uniform in its foundations? What if, on the grandest scales, it has a texture, a tilt, or a history we have not yet fully read? The true value of a cosmic mystery is not just in solving it, but in the questions it forces us to ask. the cold spot and its family of anomalies serves a deeper purpose in the grand endeavor of science. It is a persistent reminder that our understanding of the cosmos is a living, breathing work in progress, not a finished textbook. A scientific theory that perfectly accounts for every single observation might sound ideal, but in practice, it can signal a dangerous intellectual stagnation. It is the stubborn data point that refuses to fit, the unexplained whisper in the data that truly propels knowledge forward. These anomalies are not failures, they are invitations. They are the universe's way of nudging us and saying, look closer, think harder, there is more to the story. For centuries, this pattern has held true. The slight wobble in Mercury's orbit around the Sun was a tiny anomaly in Newton's otherwise flawless celestial mechanics. That small discrepancy eventually became a crucial piece of evidence for Einstein's theory of general relativity, completely reshaping our concept of gravity. The cold spot stands as a modern equivalent in cosmology, a quiet tremor in the data that suggests the foundations of our standard model might need a subtle, or perhaps not so subtle, adjustment. It keeps scientists intellectually honest, no matter how beautiful and successful our Lambda cold dark matter model is. This cold patch on the oldest map we have is a humbling testament that our cartography of reality is still incomplete. There are still blank spaces on the cosmic chart, labeled not with "here be dragons," but with "here be statistical outliers demanding an explanation." This environment fosters a necessary and healthy skepticism. It encourages researchers to question assumptions we take for granted, like the perfect uniformity of the universe on the largest scales. More importantly, it creates a space for radical creativity, for ideas that might at first sound like science fiction. The proposals of a cosmic texture frozen into space-time or a bruise from a colliding bubble universe are not wild guesses. They are serious, mathematically rigorous hypotheses born from the pressure to explain the unexplained. They are only on the table because the anomaly exists, pushing the boundaries of what we consider possible. The cold spot teaches us that science advances not by confirming what we already believe, but by diligently investigating what we cannot yet explain. It is a lesson in humility and ambition, a call to keep mapping, keep measuring, and stay open to the universe's next great surprise. The resolution to this cosmic puzzle will not come from our current maps, but from the next generation of eyes we are building to see the ancient sky. A new era of cosmic cartography is dawning, driven by ambitious projects designed to listen to the universe's first light with a clarity we have never before achieved. Leading this charge is the Simons Observatory, a suite of powerful telescopes under construction in the high, dry Atacama Desert of Chile. This remote, arid plateau offers one of the clearest views of the cosmos on Earth, far from the distorting humidity and light pollution of populated areas. The observatory's mission is profound: to measure the cosmic microwave background's temperature and its subtle polarization with a sensitivity roughly 10 times greater than the Planck satellite achieved. It will scan the sky with thousands of superconducting detectors, operating at temperatures colder than the void of space itself, to capture the faintest whispers of the primordial glow. But the ambition does not stop there. Looking further ahead, the proposed CMB Stage 4 experiment, or CMB S4, represents a monumental leap, envisioned as a coordinated network of telescopes in Chile and at the South Pole. Its goal is to map the cosmic microwave background with an almost unimaginable level of detail, using over 200,000 detectors. Together, these observatories will act as cosmic microscopes, turning their unprecedented resolution toward anomalies like the cold spot. They will not just see the spot, they will dissect it. Every subtle gradient at its edges, every hint of internal structure will be laid bare. Crucially, they will capture polarization data with such fidelity that they can perform a definitive test. If the cold spot is the fossil of an early universe texture or the scar of a bubble collision, These instruments should detect the unique, swirling polarization signature that such a violent event would have imprinted on the surrounding light. It is a search for the cosmic crime scene's fingerprint. Furthermore, their multi-frequency observations will allow for a forensic-level cleanup of foreground contamination, removing the fog of our galaxy with such precision that any remaining signal can be declared with high confidence a true feature of the deep cosmos. These projects represent more than just better telescopes. They are our best hope for transforming the cold spot from a tantalizing statistical outlier into a precise diagnostic tool. By studying its exact shape and its hidden polarization patterns, we could potentially distinguish between a cosmic defect, a collision, or a truly bizarre void. The data they gather might not just solve one mystery, it could open a new window into the highest energy physics of the universe's birth, revealing forces and events that have remained hidden for over 13 billion years. The chill in the ancient light may soon have a very clear explanation. This pursuit leads us to the very edge of theoretical physics, where the cold spot's mystery intersects with our deepest questions about reality's fabric. The most exotic explanations for this anomaly are not just ideas about the cosmos, they are potential windows into the quantum nature of gravity itself. A cosmic texture, for instance, is a direct prediction of certain grand unified field theories, a natural consequence of how the fundamental forces may have crystallized. A bubble universe collision, meanwhile, is a central feature of the string theory landscape, a framework where countless universes with different physical laws bubble up eternally in a vast multiverse. In this light, the cold spot transforms from a mere curiosity into something far more significant, a rare and fragile bridge. It could connect the observable, classical universe we measure with telescopes to the elusive, quantum realm where gravity is reconciled with the other forces. This is a profound linkage tying the largest structures we can see, spanning billions of light years, directly to physics operating at the smallest conceivable scales, trillions of times smaller than an atom. While direct, smoking gun evidence for these theories remains beyond our current grasp, the cold spot's very existence provides crucial motivation. It pushes theorists to refine their models, to derive more precise and observable signatures that future telescopes could hunt for. What specific, faint pattern in the polarization would a texture leave? Exactly what statistical profile would a collision imprint on the distribution of galaxies? The anomaly acts as a puzzle from nature, challenging the most advanced mathematical frameworks to make a concrete, testable prediction about our world. It asks whether the chill in the ancient light is a whisper from the era when gravity was born, a signal from the moment the cosmos chose its fundamental shape. The search for its origin, therefore, is not just about mapping a cold patch on a chart. It is a journey toward understanding how the universe's grandest architecture is woven from the tiniest, most fundamental threads. This deep chill in the ancient sky resonates far beyond the walls of observatories and academic journals. The cosmic microwave background cold spot possesses a rare kind of magic in science communication, a visual simplicity that opens a door to profound complexity. Anyone can look at a map and see the anomaly, a single, distinct patch of coolness on the fiery canvas of the infant universe. That immediate, almost intuitive recognition, something here is different, is a powerful starting point. It transforms an abstract cosmological model into a tangible mystery, a cosmic whodunit, written in the language of temperature and light. This accessibility makes the cold spot a perfect ambassador for the wonders of modern cosmology, inviting everyone to ponder the same questions that keep professional astronomers awake at night. What could cause such a thing? Is it a flaw, a fossil, or a message from beyond? The very act of asking these questions alongside scientists creates a shared sense of wonder, democratizing the awe of discovery. This public engagement often goes beyond passive fascination. It can become active participation through the incredible power of citizen science. Consider the monumental task facing astronomers searching for the hypothetical supervoid. They have vast digital sky surveys containing images of millions upon millions of galaxies. To map the cosmic structure in the direction of the cold spot, these galaxies need to be identified and classified, a task too immense for any small research team. This is where projects like Galaxy Zoo have revolutionized the process. By designing an intuitive online platform, scientists invited people from all walks of life to become cosmic cartographers. Volunteers would look at images of galaxies and answer simple questions about their shapes, contributing to a massive collective data analysis. In this way, the search for the void that might explain the cold spot was aided by thousands of curious minds around the world, each classification a small but vital piece of the puzzle. This collaboration highlights a beautiful truth about our exploration of the cosmos. The universe is not a secret to be unlocked by a select few with advanced degrees. It is a shared inheritance, a story written across the sky that belongs to all of us. A single anomaly, by sparking curiosity and enabling participation, reminds us that the drive to understand our place in the cosmos is a fundamentally human endeavor. It forges a connection between the individual gazing at a computer screen and the grand, mysterious architecture of everything that exists. Yet this journey through cosmic possibilities must pause for a moment of scientific caution. Among the community of cosmologists, a vital counter-narrative exists, one that questions not the data itself, but how we have chosen to interpret it. This perspective centers on a subtle but profound statistical trap known as the look elsewhere effect. To understand it, think of a simple experiment. Imagine you are handed a massive, detailed map of the entire world and asked to find the single rainiest spot on the entire planet. After a long search, you pinpoint a location with an exceptionally high rainfall record. The natural question is, how rare is this? The danger lies in how you calculate the odds. If you only consider the rainfall history of that one specific town, the record might seem astronomically improbable, a 1 in a million event. But that calculation ignores the crucial context. You searched through tens of thousands of towns globally to find it. When you account for the fact that you looked everywhere, the probability of finding some town, somewhere, with an unusually high record becomes far more likely. This is the essence of the look elsewhere effect in cosmology. We did not predict the cold spot's exact location, size, or temperature in advance. Instead, we created an exquisitely detailed map of the entire cosmic microwave background, and then scanned it to find the most unusual feature. Some researchers argue that when we properly account for this post hoc searching, the statistical significance of the cold spot diminishes. Its strangeness, while still notable, may fall within the realm of what is possible in a standard, random universe. This is not an attempt to dismiss the mystery, but to enforce a crucial discipline. The field continuously develops more sophisticated simulations and statistical techniques to recalibrate these probabilities, running millions of virtual universes on supercomputers to see how often a feature like the cold spot appears purely by chance. This rigorous, self-critical process is the bedrock of scientific integrity. It ensures that the thrilling pursuit of new physics is always balanced by a sober accounting of probability, reminding us that the most extraordinary claims require not just extraordinary evidence, but evidence that has survived the most extraordinary scrutiny. A cosmic anomaly becomes a cultural touchstone when it escapes the confines of academic papers and enters the collective imagination. The cold spot has done precisely that, serving as a fertile seed for science fiction writers and filmmakers. Its very nature, a vast, unexplained region of coolness in the universe's first light, invites narrative exploration. We now see stories featuring universe-spanning voids that are not empty, but alive with strange physics or cosmic bruises that mark the site of an ancient, catastrophic collision with another reality. In these tales, the anomaly becomes a gateway, a secret door in the fabric of space-time leading to realms with different laws or forgotten histories. This transformation from data point to plot device is a profound human tradition. Centuries ago, early astronomers peering at Mars sketched long, straight lines they interpreted as canals, evidence of a vast alien engineering project. Before that, the stars were fixed upon crystalline spheres, a beautiful and orderly model for a divine cosmos. These were the celestial mysteries of their day, interpretations of limited data shaped by contemporary hopes and fears. The cold spot is our modern equivalent, a mystery not of perception but of precision measurement, yet it fulfills the same deep need. It takes the raw, often abstract numbers from satellites like Planck and gives them a face, a scale, and a story. This cultural resonance is more than just entertainment. It reveals something fundamental about our species. We are not passive observers of the cosmos, we are meaning makers. Faced with a blank patch on the map, be it an uncharted ocean or a cool region on a microwave sky map, we instinctively fill it with dragons, with gods, with gateways, or with the intricate possibilities of theoretical physics. The cold spot, grounded in hard data yet open to wild interpretation, becomes a canvas. On it, we project our questions about isolation, about contact, about whether our universe is unique or one among infinite others in a multiverse. It allows us to explore the emotional and philosophical weight of cosmological discovery through story, asking what it means to live in a universe that might bear the scars of a violent birth or the fingerprints of a neighbor we can never truly meet. This journey from scientific anomaly to cultural icon underscores a beautiful truth. Our quest to understand the cosmos is, and has always been, a deeply human story. This conversation between the vast and the minute reveals a profound truth about our universe. While cosmologists theorize about cosmic textures and defects, a parallel investigation unfolds not in deep space, but in university laboratories. Here, in the field of condensed matter physics, researchers study the strange behavior of materials like liquid crystals, superconductors, and Bose-Einstein condensates. These are states of matter where quantum effects manifest on visible scales, creating exotic collective behavior. And within these carefully chilled samples, physicists can actually create and observe topological defects, flaws in the orderly arrangement of a material's structure. A liquid crystal display is a perfect everyday example. Its molecules align in a specific direction to control light, but sometimes, under certain conditions, that alignment can develop a kink or a twist, a localized defect that disrupts the smooth flow of information across your screen. These imperfections are not mistakes. They are inherent features of how ordered systems form when they cool or undergo a phase transition. The mathematics describing a knot in a liquid crystal's molecular field bears a striking resemblance to the equations describing a hypothetical cosmic texture in the early universe's energy fields. This is not a coincidence, it is a consequence of universal physical principles. In the lab, scientists have a powerful advantage: control. They can precisely tune temperature, pressure, and magnetic fields to trigger phase transitions and watch in real time as defects form, evolve, and sometimes annihilate. They can study the precise conditions that give rise to these structures and measure the energy signatures they leave behind. These tabletop experiments become cosmic analogies, offering tangible insights into processes we can never recreate from the universe's first moments. The feedback loop this creates is remarkable. A cosmologist might propose a model for how a primordial texture would influence the cosmic microwave background. A condensed matter physicist can then design an experiment to see how a similar defect forms in a supercooled gas, providing clues about the dynamics and stability of such an object. This dialogue demonstrates the breathtaking unity of physical law. The same fundamental mathematics can describe a defect in a film of helium cooled to near absolute zero and a potential flaw in the fabric of spacetime spanning billions of light years. It suggests that by understanding the intricate rules of order and disorder in a lab beaker, we might be decoding the very same rules that shaped the grand architecture of the cosmos. The chill of the cold spot, then, connects not just to other universes, but to the chilled experiments right here on Earth, where the universe's deepest symmetries are being tested one carefully controlled phase transition at a time. This drive to solve a mystery at the edge of the observable universe inevitably leads to a deeper question of value. Why does it matter, in a world of pressing, immediate challenges, what justifies the immense intellectual and financial resources poured into understanding a faint, cold patch on a map of ancient light? The pursuit of the cold spot is not about finding a new energy source or predicting the weather. It is fundamental research in its purest form, knowledge sought for its own sake. This endeavor carries a quiet but profound ethical dimension, a statement about what we, as a civilization, choose to value. When we fund a billion-dollar telescope in the high desert or dedicate decades of human genius to refining a cosmological model, we are making a collective bet on curiosity itself. We are affirming that understanding our place in the cosmos is not a luxury, but a core part of the human experience. The cold spot, as a focal point for this quest, becomes more than an astronomical object. It transforms into a symbol of our species' need to look beyond the horizon and ask why. This impulse to explore and comprehend defines us. It is the same drive that sent ancient navigators across uncharted oceans and inspired philosophers to gaze at the stars, seeking patterns in the chaos. Solving cosmic mysteries does not put food on the table, but it nourishes something equally vital, our collective imagination and sense of wonder. It enriches our culture with new myths and metaphors, challenges our intellectual frameworks, and humbles us with the scale of a reality far grander than our daily concerns. The ethical argument is that such pursuits expand what it means to be human. They remind us that we are not just consumers or inhabitants of a small planet, but participants in an epic, unfolding story of discovery. By choosing to investigate the cold spot, we choose to invest in a legacy of understanding, a testament to the idea that some questions are worth asking simply because the answers, whatever they may be, redefine our entire universe. The evidence, as it stands, presents us not with a single answer, but with a fascinating spectrum of possibilities. Each theory carries its own weight of plausibility and its own burden of proof. The Supervoid Hypothesis, once the frontrunner, now walks a tightrope. Its elegance is undeniable, but the cosmic census has failed to find the colossal emptiness the math demands. It remains a possible, even likely, contributor, but it struggles to stand alone as the complete explanation. The cosmic texture model offers a compelling narrative, tying the anomaly directly to the universe's violent infancy. Yet for all its theoretical beauty, it awaits a crucial piece of evidence, that telltale swirl in the polarization of the ancient light that would act as a fingerprint. Without it, the texture remains a brilliant idea in search of confirmation. And then there is the multiverse collision, a concept that stretches the imagination to its breaking point. It is the most thrilling explanation, promising a glimpse beyond the horizon of our reality, but by its very nature, it is also the most difficult to ever prove conclusively. It exists in the realm of profound speculation, a magnificent story the universe might be telling, but one written in a language we are still learning to decipher. Given these challenges, the most conservative and perhaps safest scientific position is to view the cold spot as exactly what our statistical models say it could be, a rare but permissible fluke. In a cosmos governed by random quantum seeds, we should expect every so often to roll cosmic dice that land in an unexpected configuration. This 1 in 50 or 1 in 200 chance event might simply be the universe's version of a lucky or unlucky streak. To declare it anything more requires extraordinary evidence, and that evidence, as of now, remains elusive. This stance is not a surrender to mystery, but an adherence to rigorous scientific discipline, a refusal to chase shadows without a clearer signal. Yet the story does not end with conservative caution. The cold spot refuses to be so easily dismissed. Its persistence across multiple satellite missions and independent analyses gives it a stubborn reality. More importantly, it does not exist in isolation. Remember its puzzling family, the hemispheric asymmetry and the aligned multipoles. A single anomaly might be a coincidence, but a pattern of anomalies begins to look like a clue. This association is what keeps the door firmly open to more exotic physics. It suggests that the cold spot may not be a bug in the cosmic code, but a feature of a program we have not yet fully decompiled. The investigation, therefore, thrives on this productive tension. On one side, meticulous statisticians recalibrate probabilities and refine foreground models, ensuring we are not fooled by cosmic mirages. On the other, visionary theorists run supercomputer simulations of colliding bubble universes and primordial phase transitions, searching for a signature that matches the map. This is the engine of scientific progress, a dynamic dialogue between skepticism and imagination, between what the data strictly allows and what it daringly suggests. The current state of play is not one of confusion, but of active, focused curiosity. The mystery of the cold spot has successfully framed a profound question about the largest scales of reality. It has directed the gaze of our most powerful instruments and sharpened the pencils of our most brilliant minds. We are in a period of waiting, but it is an expectant wait, like astronomers pointing a telescope at a predetermined patch of sky, knowing a predicted comet should appear within the hour. The next generation of observatories is being built for this very purpose, to gather the light that will tip the scales. Until then, the cold spot remains a magnificent question mark hanging in the cosmic background, a chill in the ancient light that continues to inspire both caution and wonder in equal measure. The true legacy of this cosmic anomaly may lie not in its solution, but in the profound shift it has already created. Regardless of whether the cold spot is a fluke, a fossil, or a bruise, its very existence has permanently altered the landscape of cosmology. It has acted less like a destination and more like a powerful catalyst, forcing the entire field to evolve in its shadow. The first and most concrete impact is methodological. To even see the cold spot clearly, scientists had to become masters of cosmic forensics, developing unprecedented techniques for cleaning the static of our own galaxy from the primordial signal. This drive for purity has revolutionized data analysis and foreground modeling, creating tools now used as standard practice across the discipline. Every future map of the distant universe will be sharper because of the meticulous work this one anomaly demanded. Beyond data cleaning, the cold spot ignited a renaissance in statistical thinking. It forced cosmologists to move beyond simple questions of whether a feature exists to far more nuanced inquiries about probability and the look elsewhere effect. How do you properly calculate the odds of something you did not predict? This challenge has spurred the development of more robust, sophisticated statistical frameworks and fueled the creation of vast supercomputer simulations, entire virtual universes generated to test just how strange a random cosmos can truly appear. The tools forged in this statistical crucible are now applied to every other large-scale anomaly, making the entire field more rigorous and self-aware. Perhaps most exciting is its role as a muse for engineering and theory. The cold spot is a primary scientific target for projects like the Simons Observatory and the planned CMB Stage 4 experiment. These billion-dollar endeavors, with their hundreds of thousands of detectors, are being built in no small part to finally solve this riddle. Their designs are pushed to new limits of sensitivity and precision specifically to capture the faint polarization whispers or the exact temperature profile that could crack the case. In parallel, theorists have been granted a magnificent puzzle. The need to explain the cold spot has given mathematical substance to once fanciful ideas, from cosmic textures to bubble collisions, demanding they make specific, testable predictions. It has provided a rare bridge between the abstract mathematics of quantum gravity and the tangible, observational world of telescope data. Even in the unlikely event that future data somehow diminishes the cold spot's significance, its legacy is secure. It will stand as a classic case study in how science progresses. It taught a generation of researchers to question comfortable assumptions, to look harder at their most beautiful models, and to dare to entertain explanations that lie at the very edge of imagination. The chill in that ancient light did more than puzzle us. It reminded us that the cosmos is under no obligation to be simple, and that our greatest discoveries often begin with a single, stubborn piece of data that refuses to fit. The strange cold spot in the oldest light of the universe remains a profound and captivating puzzle, a single cold whisper from the dawn of time that continues to challenge our most cherished cosmological models. Its story is not one of a solved equation, but of an open question, a testament to the fact that our understanding of the cosmos is a living, breathing journey. We have walked through the leading possibilities, from the elegant shadow of a supervoid to the frozen scar of a cosmic texture, and even the breathtaking possibility of a bruise from a colliding bubble universe. Each theory offers a different window into the forces that shaped everything, yet the final verdict remains suspended, awaiting the next generation of data. This investigation, in its very essence, exemplifies the relentless human drive to comprehend our place in the grand scheme. It showcases the beautiful tension at the heart of science, the dance between rigorous skepticism, which demands more proof, and boundless imagination, which dares to propose realities beyond our own. The cold spot serves as a powerful reminder that the universe is under no obligation to be simple or to conform neatly to our intellectual blueprints. It humbles us, suggesting that the magnificent map we have drawn of cosmic history, for all its detail and predictive power, likely still contains blank spaces, regions where the old cartographers might have written, "Here be dragons." As new telescopes like the Simons Observatory come online, peering into the ancient light with unprecedented clarity, we stand collectively on the brink. The next few years may bring the crucial evidence that tips the scales, transforming this anomaly from a mystery into a milestone, a key that unlocks a deeper layer of cosmic truth. Until then, the question hangs in the balance, inviting curiosity and wonder. What do you think the cold spot represents? Is it a flaw, a fossil, or a message from beyond? Share your own theories in the comments below. If you enjoyed this deep dive into one of space's great enigmas, subscribe for more journeys to the edge of our understanding. And whenever you have a moment, remember to look up. The universe is still telling its story, and we are only just learning how to listen.